call a root, a zero, a solution, or an x-intercept all has the same meaning. From Unit 3, we talked about find the zeros. That means find the x-intercepts. How many zeros can a polynomial function have? It can only have as many real zeros as its degree. So for example, a quadratic could have as many as 2 real roots, meaning 2 x-intercepts. It says, does a quadratic function always have 2 real roots? So no, I'd like you to show 3 different quadratic functions. One that's above the x-axis, one that is sitting on the x-axis, and one that's cutting through the x-axis in 2 different places. Just to show, no, it doesn't have to have 2 x-intercepts. But we learned this in Unit 3. It might have 0, it might have 1, it could have 2. Does it have to have 2? No. So a good final exam sum it all up question might be, does a quadratic have to have 2 real roots? Why or why not? So you can illustrate it, drawing a few different graphs to show no, so these are quadratics that don't have 2 real roots. This says draw a cubic function and determine how many real roots it will have. So I kind of already did this, but let's pretend to draw this cubic function that only has 1 and this cubic function that would have 3. And I would write could have 3. This one I'm going to say could have 2. So quadratic could have 2, cubic could have 3. I don't have to memorize that. As long as I know what my graphs look like, I could just sketch a graph and then figure it out counting on the graph. And then this one says draw a linear function and determine how many real roots it will have. We know that a linear function is always going to have just 1 because a line can only cross the x-axis once. It never turns around. So 1. So, I mean, if you want to draw yourself more than one example, you can draw something with a negative slope. It's only going to have 1 x-intercept. So this was talking about how many zeros it could have. So now this bottom part talks about turning points. How many turning points could a polynomial function have? It can only have as many turning points as 1 less than its degree. So that's kind of the rule. So up top, how many zeros? It can only have as many real roots as its degree. That's the rule. How many zeros can it have? Down here, how many turning points can it have? 1 less than the degree. I feel like those 2 rules are very similar, but if you draw some pictures for yourself, okay, turning point versus x-intercept. So this says, let's set the linear function. I already did this on the board just as an intro, but maybe it'll make more sense this time around. So a linear function has 0, I'm going to call them TP, 0 turning points. A quadratic function has 1 turning point. And our cubic function, it could have 0, but it could also have 2. Some cubic functions have 0 turning points. Why did I try to come up with these rules? Because I'm going to try to sketch polynomial functions. So now I know what the end behavior is doing. Can someone tell me what the end behavior of this function would be? 5x to the 6. What does the 5 tell me? What's the right side of the graph going to do? It's going to go up because 5 is a positive number. What does the x to the 6 tell me? They both go up because 6 is an even degree, like a quadratic. So all this other stuff is creating x-intercepts and bends and twists. So we don't know what's happening. But if we know that it's 6 degree, how many roots could I have? actually touch the x-axis 6 different times. How many turning points could I have? I could have up to 5, depending on how curvy this graph is. So the degree is 6, so I could have 6 roots or zeros or x-intercepts. My degree is 6, so I could have 5 turning points. So your degree and your roots are equal, and your degree and your turning points are off by 1. But it's not a guarantee. But it's telling you that if you see this graph, could that graph be a quadratic? Why? It has 3 turning points. So this could be x to the 4th, right? But it cannot be x squared because it's got 3 turning points. So it tells you, it helps you eliminate some of the graphs. So the 2 big ideas on that page were how many x-intercepts and how many turning points. Here's the little bit more important page and what we're going to be looking at today, the idea of multiplicity. Multiplicity is just how many times a factor appears in the polynomial function. So, for example, we've only looked at times when a factor appears once. X plus 1 is appearing once. X minus 2 is appearing once. We're going to start looking at x plus 1 times x minus 2 squared. So now, how many times does x minus 2 actually appear? It actually appears twice. X minus 2 times x minus 2 is x minus 2 squared. So it's actually appearing twice. I'm going to peel this piece of tape off. I don't even know why that's there. Okay. Looks messy. All right, so something can either have odd or even multiplicity, not to be confused with odd or even degree. Zeros with odd multiplicity cut through the x-axis. We're going to see what this means. So here's an example. X times x plus 4 squared times x minus 3. So this is a polynomial that's in factored form. What are the zeros that are going to have odd multiplicity? So 2, this 2 right here is an even number. But this guy has a power of 1, and this guy has a power of 1. So odd multiplicity is something with a power of 1. So let me show you on a graphing calculator. You don't have to type this in. So I'll type it in. X times x plus 4 squared times x minus 3. Here is the graph of that function. So it's a W-shaped graph. That should make sense because what's my total degree? X times x squared times x would be x to the 4th. So this is a W-shaped graph, x to the 4th. And look, it cuts through the axis at negative. Wait a second. I don't think I typed it in right. Oh, oops. Okay. There we go. There we go. It's still a W-shaped graph. So here is my leg. It goes up and then down and back up. I knew it was wrong because at negative 4 is like a quadratic. It should bounce off the x-axis. Did you get it figured out? Okay. So here I am at 0, and 0 is cutting through the x-axis. And here I am at positive 3. Positive 3 is cutting through the x-axis. So what I want you to do is we want to sketch the graph and what it looks like. So 1, 2, 3, 4. I have an x-intercept at negative 4, at 0, and at 3. So we're going to draw the same graph twice. So go ahead and draw that graph under odd multiplicity. And I'd like you to draw an arrow to these two x-intercepts. Because these two x-intercepts have odd multiplicity. It's cutting through the x-axis. Here, it's bouncing off of a quadratic function. So it says, let's take the zeros with odd multiplicity. X equals 0 and x equals 3 both have odd multiplicity. And I can see that from the original equation. X to the first power is odd. X minus 3 to the first power is odd. So this is a good review from graphing quadratics and x-intercepts and factoring. So you're going to write that at 0 and 3, we have odd multiplicity. All right, we're going to repeat that and draw the exact same graph down below. So try to make it look like the same graph that you just drew. 1, 2, 3, 4, 0, 1, 2, 3. So like kind of make it look like the same amount of bump and same graph. But this time I only want you to draw an arrow to that far left here and say x equals -4 has even multiplicity. Yeah, -4 from this one and +3 from this one. So -4 is where I'm bouncing and +3 is where I'm cutting through. So we're going to use kind of all the information that we have to be able to sketch something like this without needing a graphing calculator. So it's like you're using a detective and you're putting together all the clues that a function is giving you, because you should be able to tell some things about the graph just from the function alone. All right, so I'm going to show you an example of one that you'll be given, and we're going to use end behavior, zeros, and multiplicity to sketch the whole graph. Can I move it down to that last example? Anyone need more time? All right, so it says graph, sketch a graph of this polynomial function. So there's a couple things we need to think about first. What is the total degree of this function? This is the problem that was on your homework that we hadn't done yet. Yes, so this is x squared times x times x times x. If I put this in standard form, I'd actually have x to the 5th power. So you're counting up all the powers. This has a total degree of 5. What's the leading coefficient? So if I multiply 2x squared times this x times this x times this x, won't I still just have 2 as my leading coefficient? Okay, what is the right side of the graph going to do? And what is the left side of the graph going to do? My leading coefficient is positive, so the right side will go up. What about the left side of the graph? The degree is 5. 5 is an odd number, right? So my left side is going to go in the opposite direction as my right side. Okay, what are all of my zeros? So x equals, what would make 2x squared equal 0? This is, you gotta dig deep and remember how to find zeros in factored form. The x would be 0 here. X could be, what about from x minus 1? What would make that 0? 1. What about from x plus 2? -2. And these are the same, right? This is x plus 2, this is x plus 2. So I need to write down what is the multiplicity of each of those x values. This says x squared. So x squared, this 0, has a multiplicity that is even, right? Because its power is 2. See how that says x squared right there? So now see this x minus 1? What is its power? Its power up here is a 1. Right? So I'm going to just put a 1 right here so that you can see it. So it is odd because its multiplicity was 1. All right, trick question. What's the multiplicity of the x plus 2 term? It actually is showing up twice. So even though I didn't write x plus 2 squared, right? It's showing up 2 times. So it has even multiplicity of 2. So all that information is going to help us graph this polynomial function. So this is kind of like put everything together from this unit. So your first step is to plot all of your x-intercepts. I have an x-intercept at 0, I have an x-intercept at +1, and I have an x-intercept at -2. So you plot all your x. Let's write kind of step 1. Plot all your x-intercepts. Step 2, plot your end behavior. And then step 3 is think about your multiplicity to sketch your graph. I'll wait a minute while you write up those steps. Sometimes people don't know what to do first once they have all the information in front of them. It's kind of like overwhelming, too much information. All right, I did step 1. I plotted all my x-intercepts. So make sure you have plotted all your x-intercepts. I'll wait 30 more seconds while you write down steps 2 and 3, and then we're going to do steps 2 and 3. All right, what's my end behavior? I was told the right side goes up. So I go to the furthest right side and I draw an arrow that it's going up. And I wrote down that the left side goes down. So I go to the furthest left dot and I draw an arrow that it has to go down from there. I just have to connect this kind of S curve in the middle. There's only there's one place that's going to cut through because it's odd. There's 2 places where it's going to bounce off because it's even. So we said that at -2, it's going to bounce off the x-axis, kind of like a parabola. We said at, what did we say? At 0, it's going to bounce off again. So I'm going to kind of bounce off twice. And then finally, at +1, I get to cut through the curve and go up. So I come out, I bounce off. I don't know where this turning point is, somewhere. Then I come up again and I bounce off again. I don't know how far down that goes, but I just bounced off. And now I cut through and go up. So it said, let's look at a graphing calculator and just see. Let's see, we had 2x squared times x minus 1 times x plus 2 squared. So mine wasn't that far off, right? Bounce off, and then go up. So I had never looked at that graph before. So only from x-intercepts, end behavior, and the multiplicity, I got pretty close to what the graphing calculator, right, told me. Even is bouncing off like a quadratic. See how I remember it because this just says 2x squared. So it's almost like there's a little quadratic function happening at that point. And then I think of linear as it cuts through the x-axis. 2x to the power of 4 is even, so it would also bounce off again. All right, let's look at a couple examples together. Page 608. This is hard. This is like the last section of the year for you. So it's a little bit of synthesis. So let's look at example 1 together on page 608. Think about all these questions that you'd have to answer. The first question is asking you, what is the total degree of the function? So add up all the powers. This is x to the first. I'm going to write a little 1 right here. This is x squared, and this again is x to the first, right? So if I add up all those powers, I have a total degree of 4, right? 1 plus 2 plus 1 is 4. All right, all I need is this number 4 to answer these next 2 questions. That was on the first part of the resources that we did. How many x-intercepts could I have? And how many turning points could I have? I could have 4 x-intercepts because it's the same as the degree, right? Linear has 1, quadratic has 2. How many turning points could I have? I can have 1 less than the degree, right? Like a quadratic only has 1 turning point. A linear function has 0 turning points. That was kind of part 1 of what we did today. Part 2 of what we did today was finding the x-intercepts and then sketching the graph with their multiplicity. All right, so let's see. What are the x-intercepts? I'm actually going to just draw arrows over here. I think it's easier if you see what the x-intercepts are over here. What would make that 0? When x equals 0, what would make that 0? When x is -1. Do you remember how to solve when you have like 2x minus 3? What do I do to solve 2x minus 3 equals 0? We had to do this in Unit 3 this year. So you would write out 2x minus 3 equals 0. You would add 3 to the other side. So I have 2x equals positive 3. Sorry, I kind of ran out of room here. Then I would have to divide by 2 on both sides. So x would have to equal 3/2 or 1.5. You kind of remember that from our study of quadratics. So my 3 x-intercepts are x equals 0, -1, and positive 3/2. I have 3 x-intercepts. I'm going to sketch the graph underneath here, but what's the multiplicity of each one? So let's see. If I go back over here, where were my odd multiplicities? This one had a 1, and this one had a 1. So at 0 and at 3/2, 0 and 3/2 were odd. So I'm going to write 0 and 3/2 were odd. And at -1, I had even multiplicity. So where's it going to bounce off? It's going to bounce off at the -1, right? So I'm going to plot my graph. 0, 1.5, and -1 are my x-intercepts. So I plot my x-intercepts. I never wrote down my end behavior, did I? What will the right side of my graph do? What would be the leading coefficient? The leading coefficient is positive, isn't it? So I'm going to go up on the right. What did I say my degree was? My degree was 4. So they're both going to go up, aren't they? Because my degree is an even function, degree of 4. Which do I bounce off at? -1 had that x plus 1 squared, right? So it's going to bounce off, cut through, cut through. So I bounced off, I cut through, and I cut through. And see how all my information gets connected? My end behavior, my zeros, and my multiplicity have to work together to make a graph, or else one thing might be off. So, like, you are a complex thinker if you can put together that big puzzle. That is a big puzzle. So on your test on Friday, I would lead you through each step. So I would give you this question at the top, and then part A would be like, what is the degree of this function? Part B, what is the right end behavior? Part C, what is the left end behavior? Part D and E, find all the zeros, find their multiplicity. So I think if you practice those steps over and over again, it'll start to make sense. But right now, that is a daunting problem. That's a big problem, a lot of steps. But I think it helps you learn degree, end behavior, x-intercepts that we learned from quadratics. Like, I really like this unit. It puts together a lot of your information in order to form something. You're forming a product at the end, a graph, right? So I'd like you to try, I'm not going to set you on your own, but I'd like you to see what you would answer for question number 2. Yeah, I'd like you to try to sketch a graph. You can wait to do the graph, and you can check your answers to only do this row. So Killian and Jake, you guys need to pass. So this has a power of 1, x to the first right here, and this has a power of 5. So my total degree is 6. If I was going to multiply all this out into standard form, it would have a degree of 6. So there are 6 possible x-intercepts and 5 possible turning points. Remember, these are always the same, and this is always one less. My x-intercepts are at +5 and at -2, right? +5 from this, -2 from this. They both have an odd multiplicity. This is showing up once, and this is showing up 5 times. So 1 and 5 are both odd numbers. So they both have, so I can write 5 and -2 have odd multiplicity. So now I'm going to try to sketch this graph. So I'm going to plot -2 and 2, 3, 4, 5, +5. And I'm going to think about the end behavior. -4 is my leading coefficient. So that tells me I'm going to go down on the right side of this graph, right? -4 goes down. Now I think about my degree. My degree was 6. 6 is even, so they must both go down. The left side has to do what it's told. You always do the right side first. The left side either does the same thing or goes in the opposite direction. So you always do the left side second. And then we said odd multiplicity, so it must just cut through, do something up here, and then come back down. We don't really know what it does in the air. We just know that eventually it comes down, so draw it however you want. And I looked at the graph, and the graph kind of does a little twist, but it pretty much looks like that. So it does this little, like a little twist right here, cuts up. It might do something up here, and then it comes back down. Okay, the last one for today on this page, and then we're going to look back at a little bit of factor. I'm going to give you about 10 minutes to do either tonight's homework on division and get help or that factoring practice that's due. This last question says, if x minus 1 is a factor, if it's a factor, we want to find what this is in factored form. So what you're going to do down here is do a little bit of division. Right? So they're saying x minus 1 is one of your factors. Find your other factors. So take a minute and do some division. You should not get a remainder. You should get a remainder of 0. Mm-hmm. The only thing is I made it not a factorable quadratic at the end. So I'm not going to be able to graph this thing fully, but x squared plus 3x plus 8. I think last year I was using this particular example with advanced, and they had to do the quadratic formula, and I'm not going to revisit quadratic formula. We just did it like one time. So you could actually figure out your other x-intercepts using the quadratic formula for this one. But that aside, we should be able to answer these other questions. The total degree was 3, right? This was a cubic function. So I know that it could have 3 x-intercepts, but only 2 turning points. X cubed was standard form, right? This is x times x squared would be x cubed. This is factored form. You could always go back to standard form to figure out the degree. I'm not going to graph it, but I know that x equals 1 is one of my x-intercepts. I would have to do quadratic formula to figure this one out. So 1 has odd multiplicity, right? Because it's x minus 1 raised to the first power. So that's all I would have you do on a problem like that. So on all that new stuff,